Have you ever just stared at a blank screen and wondered, how does an engineer actually design a machine from scratch? Well, today, that's exactly what we're going to do. We're going to dive into kinematic synthesis and learn how you can take a simple motion requirement and turn it into a real, working four-bar linkage. And that really is the fundamental question, isn't it? We're not talking about just analyzing a machine that someone else already built. We're talking about the act of pure invention, creating something new to do exactly what we want it to do. That whole process of defining the geometry of a mechanism to get a specific output motion, that's kinematic synthesis. So let's get one thing straight right away. There's a huge difference between analysis and synthesis. Analysis is kind of like being given a finished math problem. You have the mechanism, you have the inputs, and you just solve for the output. There's one right answer. But synthesis? Oh, synthesis is where the magic happens. You start with the answer, the motion you want, and you have to invent the machine that creates it. It's the very heart of engineering creativity. Now, to tackle a creative challenge like this, we're not just going to be guessing. We're going to use an incredibly powerful tool that's probably already sitting on your computer. It's called Geometric Constraint Programming, or GCP, and it's the engine that drives pretty much all modern CAD software, like SolidWorks. So what is this GCP thing, really? Well, when you're sketching in a parametric program, every single line, point, and circle you draw is actually part of a giant system of equations. And then, when you add a constraint, say making two lines parallel or tangent, you're literally just adding another equation to the list. The software solver then crunches all those numbers and finds the one geometric solution that makes every single one of those conditions true at the same time. It's pretty amazing. So to harness that power, we follow a simple, repeatable, four-step recipe. It's our game plan. First, we lay out everything we already know, like where the fixed pivots are. Second, we actually construct snapshots or instances of our linkage in each of the key positions we need. Third, and this is crucial, we apply equality constraints. We tell the CAD program, hey, this link has to be the same length in all these different positions. Finally, once the solver works its magic, we extract the dimensions it found and we verify that the whole thing actually moves correctly. This is our roadmap for inventing mechanisms. Okay, enough theory. Let's apply this workflow to a real-world problem. Our quest today is to design a crank rocker mechanism. And this is a true workhorse linkage. You see these things absolutely everywhere. Now, for a crank rocker, we're usually aiming for two key performance goals. First, there's the rocker amplitude. That's just the total angle the output link swings back and forth. And second, there's the time ratio. This one is super important for things called quick return mechanisms. I mean, think about your car's windshield wipers. You want them to sweep across the glass nice and steady, but then snap back really fast, right? Or imagine a giant rock crusher. You want a slow, powerful crushing stroke and a quick return to get ready for the next rock. That's all controlled by the time ratio. All right, lean in, because this is the aha moment. This is the single geometric insight that unlocks the entire synthesis problem for us. A rocker, that's our output link, hits its two extreme positions, the very ends of its travel, at the exact moment that the crank and the coupler line up perfectly. They become collinear, either stretched out in a straight line or folded back on top of each other. That specific geometric condition is the key we're going to use as a constraint in our CAD model. Okay, so theory is great, but let's actually see this thing in action. We're about to walk through a step-by-step construction of a crank rocker using all the principles we just talked about. Let's build something. So here's our design brief, our mission. We need a mechanism with an 80-degree rocker swing, a 3:2 time ratio, and the ground length has to be 2 inches long. Now, the very first thing we have to do is translate that time ratio into a piece of geometry we can actually draw. Using the formula you see here, a time ratio of 1.5 or 3:2 gives us what's called an imbalance angle, alpha, of 36 degrees. Remember that number, 36 degrees. It's going to be critical for our construction. All right, now we build it. Step 1, we draw our 2-inch ground link, and then we draw the rocker in its two limit positions, exactly 80 degrees apart. Step 2, we sketch in two lines that will represent our coupler, one for each of those limit positions. Step 3, here's the magic. We apply that collinearity constraint we just talked about. We force the crank pivot, the end of the crank, and the end of the rocker to all lie on a single, straight line for each of the two positions. Step 4, we tell the solver that those two coupler lines we drew have to be equal in length. And finally, step 5, we set the angle between those two big collinear lines to our 36-degree imbalance angle. And boom,
the sketch turns black. The solver just figured out all the necessary link length for us instantly.
So, are we done? Not quite. And this is a really important step. Right now, we just have a static sketch. It's calculated the right dimensions for us, but we haven't actually proven that it moves the way we want. We need to verify it. I want you to think about it this way. The synthesis sketch we just made is a static calculator. That's all it is. It solved a really complex geometry problem for us. Now, we have to take the answers from that calculator and build a completely separate functional model to actually test its motion, its dynamic behavior. You can't skip this part. And the good news is, this procedure is super straightforward. We just start a new sketch right on top of our calculator sketch. We use it as a template. We draw a brand new, clean 4-bar linkage. Then, for each link in our new, movable sketch, we just add an equal constraint, telling it to be the same length as the corresponding solved link from the calculator sketch underneath. And just like that, you have a fully functional model. You can actually grab the crank and drag it with your mouse to see for yourself that the rocker is swinging exactly as we designed it to. So let's just take a step back for a second and appreciate what we've just accomplished. This isn't just some nifty CAD trick. What you've just learned is a fundamental engineering skill. It's like a new superpower. Look, the big takeaway here is that you've leveled up. You've gone beyond just analyzing mechanisms that other people designed. You now have a systematic, repeatable method to go from a list of performance requirements, a wish list of motions, directly to a functional, fully defined design. This is the whole point of kinematic synthesis. It's the creative act of inventing machines, and GCP is the modern tool that makes it possible for all of us. You've basically unlocked a whole new way of thinking about design, working backward from the result you want to the physical thing that creates it. You now have the power to translate these abstract goals into real, concrete, functional motion. So the only question left to ask is, what are you going to create next?